Okay, welcome. Another term, another semester, another module. So, System Devices 2 Networking. So, we're going to have a look at what we're going to do this semester. And not to give the game away, we're basically going to build some networks. Okay, so you probably know me from Sys1. So, my name's Mike Freeman. My office is 131. All my contact details are listed there. So, if you have any questions, do pop round. Don't leave it to the last minute. I'm always happy to chat. All teaching material, as always, is on the VLE. The slides are a teaching resource, so don't think of them as something you have to memorise. Their intention is just simply to illustrate the concepts, so hopefully by reading through those slides you'll get a better insight into the topics we're looking at. And as it does say down the bottom there is a lot of documentation with networks. So networks are standards, networks are protocols. So there's a lot of documentation, and those documentations are typically referred to as RFCs, so requests for comments. And they describe every nuance of the protocol that we'll be looking at. And we will be looking at these, but we will only be skimming through. So we're not going to dive into all the nuances of DNS, etc. But we'll look at the basics. We'll get a good understanding of what's going on there. So, as always, the learning outcomes for this module are on the module descriptor page, so do have a look there. Sys2 is divided into two sections. So you have Sys2 OS, operating systems, taught by Poonam, and you have Sys2 networking, taught by me. And I would describe them as two 10-credit modules under a 20-credit Sys2 umbrella. My personal opinions are that how you design an operating system and how you design a network are completely different beasties. There's no real links between them. So how you manage the software and hardware that makes your computer, how you design an operating system is one problem, and how you communicate across a network, across a communication channel is a different concept. So they are completely different things. Obviously an operating system does use a network, but how you design a network and how you design an operating system, completely different journeys. So to read the module descriptor, this module introduces students to the core concepts of computing networking. It starts by covering the layered network model and discusses the utility and motivation for such an approach. Services that are layered on this model, such as sockets, DNS, TCP/IP, are detailed, and students will develop software to experiment with these features. After taking this module, students will have an understanding of all kinds of computer networks, including the internet. Some truth there. Obviously, the internet is a very big and scary place. So I wouldn't say at the end of this module you'll know all the nuances about what the internet is. But yes, you will be able to set up, use and debug a basic network, and you'll understand what protocols are used for the applications that use it. Okay, as you probably guessed, I believe that teaching is a hands-on process. So just as Sys1, the core design feature for me when developing this material was, what skills do you need going forwards? So what skills do you need to use a network, to build a network? What skills do you need to write software that will then use that network to communicate with other networked applications? So that's the focus for me, using a network. Not so much of the analysis of bandwidth and all those other things that you do need to know, but I think that's more of an advanced module rather than an introduction module. So this is an introduction to networking. So what does that mean from a timetable point of view? What does it mean kind of working at that coalface? So here we have our semester divided up into our weeks. So as I say, Sys2 is effectively a 10-credit module, so that's 100 hours worth of work. So we have 6 recorded lectures. So in week 1 we will have this pre-recorded lecture and the lecture 2A, where we start to look at the application layer in our protocol stack. So each week we'll have some pre-recorded lectures that you can access through the VLE. We'll also have a 2-hour practical session where we get to apply that knowledge on our hardware test benches to actually build some networks. In addition to that, we have a 1-hour lecture review session where I'll go through the lecture quizzes. So embedded into the lectures, there's some exercises and quizzes that you'll need to do in your own time. And I will be doing some demos of the hardware and software you'll be actually using in the practicals. So giving you a heads up of what you'll need to know to do those practicals. So do make sure you attend those sessions or watch them using the replay system. So as you can see in this timetable, semester 1 is divided up into kind of 3 basic chunks. So you have weeks 1 to 5, then we have a break for 1 week, reading week, then we have the second section from 6 to 11, then we have our Christmas vacation, and then the exam period. So the exam, the assessment for SIS2 networking is coursework. So at the end of each practical session, there are some assess questions. You can do those in the practical session or in your own time. So you can come back to lab CSE 168, 169 in your own time to finish off any of those exercises. And there'll be a mix of tasks. There'll be some bookwork tasks they can do anywhere. There'll be some practical tasks where you'll need to take screenshots of stuff running. And there'll be some programming tasks where you write some code to transfer some data across the network. For example, using TCP and UDP. So during the semester, you'll write up your answers to each of these questions, and you'll submit that as one PDF report and a collection of Python programs after the Christmas vacation. So in week 12, roughly. Obviously, the specific submission dates and criteria will be announced on the VLE. Okay, so why do we need to know about networking? Why is it important? So what we got here is a timeline of processor development. Depressingly, I know most of these processors, so I started off with the 6502. So if you look right down the bottom, 1970s, 1976-ish, you can see right at the bottom there, the 6502. So that was in my Commodore 64. I suppose technically it'd be a 6510, but that type of instruction set. So you had a basic computer, so very, very, very comparable to the simple CPU version 1D. So over time, to increase the processing performance of our architectures, we took the simple approach and we just moved to the next silicon technology. So each time we wanted a faster processor, yes, there were architectural improvements to that processor to add different features to improve its processing power, but the key driver there was clock speed. So you went to the silicon fab plant and used a smaller transistor effectively, and you could clock it faster. And if you had a higher clock speed, obviously you can execute more instructions per second. The downside to that one, eventually you get very hot bits of silicon. So every time you get a clock transition, you dissipate a little bit of power. And obviously the more clock edges you have per second, the higher the frequency is, the more power you dissipate and the hotter they get until they melt. So there's a fundamental limitation for our silicon technology. Yes, you can keep making those transistors ever smaller and smaller, so you can get more on a chip and clock them ever faster and faster, but you do need a few atoms to build your transistor. So if you keep making it smaller, eventually each building block of your transistor becomes a single atom, which obviously is very difficult to build. So we reach a limit. So how do you overcome that limit? Well, we move to the core architecture if you follow your Intel beasties. So I think it's an i7, a bit of an old machine now, but you can see it's silicon die shot. So if you look from left to right, you have that big blue blob, that's your graphics, that's your integrated graphics unit, and then you've got some yellow blobs, that's your 6 processor cores, and you've got some memory interfaces and other logical bits slapped on the end there. So we're no longer got one processor core that we're ever clocking faster and faster and faster. We've gone to a parallel system. We've gone from one processor to multi-processor to a multi-core architecture. And that comes with its own problems. So as we saw in SIS1, the typical communication mechanism between the processor and its memory is your bus. So you've got a system bus. But you can't keep bolting on processor cores to a bus. The bus will get ever bigger and bigger. Effectively, the capacitance of that one will limit its clock speed. Basically, the loading you're placing on that one communication channel. So again, we hit bottlenecks in our silicon. And in this sense here, a communication link. So we can't keep adding processor cores to a processor, because we just shift the problem now to how do we pass data between these processing cores. Now, one way of doing that is obviously across a network. So rather than connecting our processor cores to a bus, we can connect them to a network. And many years ago, when I used to do some FPGA work, we sort of start to see that one coming in on bigger FPGA designs, so where you'd have a network on a chip. But more typically, we're looking at networking computers together to increase our processing capabilities. And you can see that in modern kind of supercomputers. So as you can see here, we have an example of NASA's supercomputers, but it kind of looks like just in an air-conditioned shed. It doesn't look so iconic as your kind of Cray 1 supercomputer back in the day. But maybe I'm just saying that because I'm old. Okay, so this machine here is basically made up of multiple processing nodes. So what you have, so I think you've got 2 20-core Xeons in each rack with a silly amount of memory, and they're all connected to each other via 100 gigabit links, and you kind of put those all together and you get a most impressive parallel processing machine there. And what allows you to do that one, obviously, is the networking. So you have to construct a network to allow you to communicate the data to where it needs to go, when it needs it. And that's not a trivial task. So developing the networking architectures needed in these data centers is an art form in its own right. We're not going to be looking at those in this module, but this is your starting point to the journey to these more complex networks that you can see here. A bit of a side note here. In a past life, I used to program systems built out of transputers. So back in the day, kind of in the 80s, we had this processor, the InMOS transputer, and you used to program it in Occam, a language that's not used anymore, but I thought it was a very elegant language. So you'd have these processors, and you'd then mount these on modules. So you can see you've got your processor plus some memory. And each transputer had 4 communication channels. It had a north, south, east and west link, so you could build big meshes of these processing nodes to solve your problems. And one thing I learned about parallel programming is very, very tricky. So not a skill I would say I ever mastered. I always seemed to write software when you distributed it across this big transputer network. So you'd have, say, 100 of these processing nodes all working in parallel to solve that common problem. I had the knack of making my software run a lot slower. So going back to our NASA supercomputer, the communication links are the key. That's the thing I found with our transputer networks, is you've got to figure out how to communicate that data effectively. Otherwise, you've just got a lot of processors sitting around doing nothing for most of the time. So yes, definitely, I take my hats off to the people who set up these systems. It's a tricky beast. It's a tricky thing to solve. And parallel programming in general is just a skill, like I said, I never mastered. Another obvious reason to learn networking is just the world we live in nowadays. Everything is connected to everything. I mean, classically it was your PC was connected to the internet. Now it's your fridge, it's your phone, you name it. It wants a network connection, which is often very secure. So if you know how to set up a network, that's a very useful life skill, even if you don't take it up professionally, because we live in that ubiquitous computing world. So knowing about networking is a handy skill. And to show that one, we have the Opti project. So you can see here we have a graphical representation of the internet. So if you'd like to find out more about that artwork, there's obviously a wiki page for that. So if you go to this webpage, you can find out more how they kind of map the internet. So mapping all the routes between the various networks of networks that makes the internet. But the key reason for showing this one is it just starts to look like a brain, doesn't it? It's sort of like the world is becoming self-aware. It looks like a medical scan of a human brain. AI, Skynet, sci-fi films have warned us of the joys to come. Right, yeah, so hopefully I've convinced you now that knowing something about networking is a good skill to have. But where does it all start? Well, for me, it started in the 80s. So I had a modem, a modulator, demodulator, which is perhaps a bit before your time. So internet connections were back then made across telephone lines, so proper telephone lines, not the digital telephone exchanges we have nowadays. So your voice was sent as an analog signal down those wires. So to represent our voices, obviously if you're from your hi-fi backgrounds, you'll know that, yeah, you're typically looking like 20 hertz to 20 kilohertz. It's the full range of frequencies the human ear can hear. But as we will see later, to maximise the number of signals we can send down these telephone lines, we need to limit the bandwidth, the frequency range used to represent the human voice. So typically it was around about 4 kilohertz, a few hundred hertz to 3.4 kilohertz. So we lost some of that range. So you didn't quite sound the same when you were on the telephone. And that's because of the frequency limiting. So as I say, those analog signals were sent down those copper wires from your one telephone all the way through the exchange to the other telephone. So in the 80s, we saw the expansion of this strange thing called the internet. And the main driving force for me was mail, so email. So there became a need to connect home computers to the internet, to this network of networks. So to do that, we need to send digital data down these analog phone lines. We need a way of converting the ones and zeros, our digital data, into tones. So this is where your modulator, demodulator comes in. The first devices to do that were acoustic couplers. So back then, all phones looked like this, and you had a big handset. So you had a loudspeaker here that will couple to the microphone that is in the handset to allow you to send tones down the wire. And obviously here you've got a microphone coupled to the loudspeaker in the handset to allow you to receive signals. So as we all know, sci-fi films are the best films. So you'll probably recognise this from The Matrix. So the original Matrix film. So when Neo first leaves the matrix, I guess, technically, they use an acoustic coupler to connect to the matrix. So what this means is you will hear sounds like this. And obviously what that is the digital data being converted into different tones to represent the ones and zeros and being transmitted down that copper cable. Obviously over time we moved away from these acoustic couplers as these devices would pick up any background noises. So we moved towards self-contained modems, as you see down the bottom here. So effectively do exactly the same thing, but are a lot more compact and a lot cheaper to produce. To have a look at these concepts in a little bit more detail, we can simulate these analog signals using SPICE. Oh, goodness me. So simulation program with integrated circuit emphasis, I think, from my memory, but basically an analog simulator. So we can look at what happens to a digital signal if you were to transmit it down a transmission line, so you see the attenuation, and we can look at some simple frequency shift keying encoding, so how we represent our ones and zeros as tones. So we'll have a look at that one in the review lecture, so we'll see how we can use SPICE. So now we have a basic technique for transmitting digital data across our phone lines. But because the phone lines are limited to roughly 4 kHz bandwidth, that limits our bitrate to a few hundred bits per second. However, over time, we came up with some ingenious ways of encoding our ones and zeros. So we moved away from frequency shift keying to phase shift keying. So a more complex way of encoding our ones and zeros, but it meant we could get more bits per second down that limited channel bandwidth. So we pushed the limits up to around about 56k bits per second, so 56,000 bits per second. So still not up into megabits as you expect nowadays, but we had a technology where we could read emails, and back then there wasn't that much on the internet. So the question then arises, how do we increase our bitrate? So how do we get more bits per second down those copper wires? And the solution is to move the exchange closer to your house. So if you can shorten that distance between your home and the exchange, you can start to make use of those higher frequencies. So we start to see the rollout of digital subscriber lines, so DSL modems. So I suppose more technically asymmetric digital subscriber lines, I mean, in the sense that they have a different upload and download speeds. So these still connect to copper wire, but because you're transmitting across a shorter length of wire to a local exchange or a box in your street, the attenuation of our signal is a lot lower. So effectively what they do is they break up the frequency band from 25 kHz up to 1 MHz into a number of 4K modem channels, if you want to think of it that way. From memory, I think around about the 25K to around about the 140K region is for upload, and from around about 140K hertz up to 1 MHz is for downloading. So you can see there's more 4K channels, there's more frequency range for downloading than there is for uploading. That's where you get your non-symmetrical upload and download speeds, which is normally perfectly fine for the home user. Typically you're downloading more than you'd be uploading. So again, things have moved on, but typically you're looking at 10 megs down and 1 meg up. It very much depends what you've got connected to your house. Obviously, if you're in town and you've got a fibre subscriber, you get fibre to your home, or FTTH. So the advantage of fibre, obviously will allow you to run at higher speeds, but the key thing here is its noise immunity. So because you're encoding the data as optical pulses down a fibre optic cable, it's immune to electromagnetic interference, which obviously the copper cable isn't. It will pick up crosstalk from other cables or noise from other electrical sources. And obviously it's your signal to noise ratio that limits your top speed. As you start to send your data faster down that cable, you'll start to use those higher frequencies, your cable will start to attenuate those, and you'll reach a point where you can't tell the difference between signal and noise, and that's where you start to lose data. So going to fibre cable removes all that electromagnetic interference issues, because obviously we're dealing with pulses of light down cables. So again, speeds may vary, but typically it was 100 megabits down, 10 megabits up. But again, with the move to fibre to premises, FTTP, then obviously you get what you pay for, so you can get a lot faster than that nowadays as well. So we start to think about how we start to communicate across our cables, but I want to take you slightly back in history to the 1950s. So Tap 1, the first telephone line across the Atlantic. So not the first telegraph line, so we were sending telegraph data across the Atlantic long before then, but the first telephone lines. So back then, to send those audio signals down those cables, you needed underwater repeaters, so you needed to boost that signal, because obviously the cable would attenuate those audio signals, so it'd be very quiet by the time we got to America. So you needed to boost those signals at regular intervals to ensure that the signal got to the other end. So you might be asking, Mike, why are we looking at this telephone line example? Well, it's a nice way of introducing the ideas of circuit switching and packet switching. So the question was, how do you connect a phone in York to a phone in New York? And the way we did that was through circuit switching. So literally, you had a load of switches that connected intermediate lines from one user to the other. So you start to make a call on your home phone, and that would go to your local exchange. At the exchange, you'd have a load of switches. Struggle on this one. Stroker switches, but basically electromechanical switches. So back in the day, phones used pulse dialing. So what that means is that every time you entered a digit, you send a pulse down the wire. So if you entered digit 0, it sent 1 pulse. If you entered digit 1, it sent 2 pulses, and so on. So if you entered a 9, it sent 10 pulses. And it could roughly send about 10 pulses per second. So you can imagine from your phone, you've got a line to the exchange, and let's say it's coming in here. So if you send 1 pulse, this switch would move 1 position, connecting you to the next line. So it would connect you to the next switch. Then you'd send the next digit of the phone number. So say that it was a 2, and then it would move 2 positions, this one here. So you can see by sending a series of pulses down the wire, you can configure the circuit, you can configure these switches to connect the correct sequence of lines together to connect you from one telephone to another telephone. So we're creating a circuit, we're creating a direct link from one phone to the other phone. And obviously, whilst you were in conversation with that person across that circuit, it was fixed. No one else could use those lines. You get full control of that circuit. You get full control of that line, so you can push all your data or your audio signals down that wire whilst you're using it, and no one else can use it, which has its pluses. But the downside, obviously, is it's very expensive because you need a lot of wiring if you want to have multiple calls going at the same time. So old-fashioned telephone network was a classic example of circuit switching. One method of creating a communication network. So if you wanted to create communication channels between particular computers, you could switch that network, you could make that phone call an end-to-end connection that would be maintained for the duration of the call, for the duration of that data transfer, and you're guaranteed to get the full bandwidth of that channel. So from that perspective, that was its main advantage. Obviously, downside, if you're not using that channel at any particular moment, that's wasted resource. Someone else could be using it. Again, another problem that you had to overcome was that at certain points in that circuit, you'd have limited communication links. So you can see in this example here, you've got 6 cables laid between England and America. So if these were being used exactly as I previously described in the case of a circuit switch network, then only 6 people could have calls between America and England at any one time. So we need to start to think of how we can more efficiently use these communication channels. And one way of doing that is frequency division multiplexing. So if we took our telephone example again, we know that each telephone will be limited to a 4K frequency range. However, by using a modulator, we can move that 4K channel to any other part of the frequency spectrum, as you can see here. So here we have 3 phones, each allocated a 4K range of frequencies to represent the audio tones, but we can shift those up to different frequency ranges. We can then add those signals together electronically so they can all be transmitted down the same communication channel at the same time, and when they get to the other end, we can filter out the specific frequencies we're interested in and shift those back down into the audible range so that they'll be received at the telephone at the other end. And that's the way to think about those DSL modems. So you think about that frequency range being broken down into 4K chunks. Each is effectively a modem, transmitting and receiving 56k bits per second, but you've got multiple of those all happening at the same time, all being transmitted down your copper phone line between yourself and the exchange. So this is one method of sharing that communication channel by using frequency division multiplexing. Or in the case of the DSL modem, we can increase our bandwidth, as we can use each of those 4K channels to transfer data. Obviously there's a slight complexity of to split the data over those multiple channels, but that's handled obviously by your internet service provider. Handled by your digital subscriber line access multiplexer, or DSLAM. As with anything, there's a few complexities using this technique. Obviously your communication channel needs enough bandwidth to handle all these communication channels. Also, you need a little bit of frequency to separate these channels out. If you have them too close together, obviously you get crosstalk. You'll have communication channels interfering with each other. And you used to hear that in the old-fashioned telephone lines. If you kind of listen quietly, you could hear other voices on the line when this technique was used. Another technique to allow you to share a communication channel is time division multiplexing. So rather than dividing the frequency space up into chunks, we allocate specific time slots to each host so they can only use the network during their allocated time period, their allocated slot. So within that slot, they get the full frequency spectrum, they get the full communication bandwidth, but outside that time slot, they have to remain quiet. So in this example here, we have 3 hosts, 3 computers, wanting to connect to 3 servers. So you can see here that the communication is broken down into frames, and these frames contain 3 time slots, and each machine is allocated one of those time slots. So you can see in the first one here, everybody wants to communicate. So host A is using its allocated time slot, then B, then C, transferring the data to the various machines they want to talk to. In the next time frame, however, A is finished communicating, so his slot is free. So that is just unused time. So again, not very efficient, but B and C are still communicating. And in the final frame, we can see only B is communicating, so the slots allocated to A and C are not being used. So this is an example of synchronous time division multiplexing, or TDM. So when everybody wants to communicate, we hit our full efficiency quota, but when hosts don't want to communicate, then obviously we have some dead time, and that's where asynchronous comes in. So asynchronous TDM. So we look at using different techniques to reallocate these slots to people who do want to communicate. But the key thing to note here is we're sharing the communication channel by breaking it up into time slots. Okay, here we have a quick quiz for you to do in your own time. So we're looking at circuit switching. In this example here, we have 4 groups of computers. Group A, Group B, Group C, and Group D. And they're connected to a shared network. That is made up of multiple communication channels, or circuits. So as you can see here, from A to B, we have 10 circuits. We have 10 cables. From B to C, we've got 15. From C to D, we've got 12. And from D to A, we have 20. So in this example here, each connection takes 2 hops. So if you have machines from Group A, they will connect to Group C, B will connect to Group D, C will connect to Group A. So each connection, just for this example here, it takes 2 hops, and the connections are made clockwise. So the first connections are made by Group A to Group C, then the next set of connections are made from B to D, and then from C to A, etc. So knowing those limitations, knowing this setup, how many power connections can be made? So how many connections can be made in this scenario? Also, if each communication channel can transfer 1.5 megabits per second, how long would it take to transfer 1 kilobyte of data from a machine in Group A to a machine in Group C? So connection-orientated networks such as circuit switch networks are great for real-time applications because you get the full bandwidth of that channel. So as long as you're connected to that channel, as long as you're connected to that circuit, it's yours, and you get the full communication bandwidth. Obviously, the downside is typically you don't use that channel all the time. You'll have peak periods where you do, but sometimes the channel will be idle. That results in poor utilization. So one way of overcoming that one is to use packet switching rather than circuit switching. So here we're moving some of the intelligence away from the initial formation of the connection to embedding that intelligence into the packets that we're transmitting across this network. They have embedded in them the data that the switching points need to know where this communication packet is going, which obviously we didn't need in a circuit switch network, because obviously when the connection is made, you've just got that point-to-point link. You don't have to do anything else. It's already set up and good to go. Whereas packet switching, the movement of a data across the network is a little bit more dynamic. Decisions can be made by our new switching nodes to which channel should be used. Our packets, our data can take different paths now across our network, depending on what resource is available. So not to break with tradition, the typical scenario used to explain packet switching is a person posting a letter. So you're at your home and you want to write a letter to somebody else. So you put your data inside an envelope, your message inside an envelope, and obviously then you write on the outside the address that you would like this letter to be sent to. You then put that letter into a letterbox, and that will be picked up by your postman and sent to the sorting office. Obviously, how it gets to the sorting office, you do not know. You do not care. It could be go by van, by air, by ship. But eventually you'll get to a place where somebody looks at the envelope and works out where it needs to go next. And again, they'll put that envelope into the correct sack, and then again that will be sent across a different communication channel, in a plane, or in a van, or again by some means, and eventually it'll be delivered to the end point. But hopefully you can see here the difference is we're not setting up the communication link beforehand. At each hop, at each point in this transfer, because it may go through multiple sorting offices, someone looks at the envelope, someone looks at the address to work out where it needs to go next. So we would describe this type of network as a connectionless network. So as I say, there's no pre-made connection made before data is transferred. And another key thing to spot is store and forward. So the envelope is stored at different points along this communication path. So when you initially post the envelope, it's stored within the postbox. And when the postman collects it, it's forwarded to the next point where it's stored in another sack, for example, before it is processed. So your data is transferred at the packet level, at the envelope level. You're not transferring a fragment of the envelope at a time. It's all or nothing. So the whole envelope is transferred to the next stage of our packet switch network. Again, just kind of show the differences between circuit switching and packet switching. We have this pneumatic mail delivery system that they used to have in big department stores, for example. So each one of these tubes is a pneumatic line where you could send a capsule here. So you'd have a positive air pressure at one end of the tube, which would then push this container down the tube until it reached one of these sorting points. At those sorting points, someone's got to make a decision where it is going to. So if this was a circuit switched network, you'd have a tube that would connect two tubes together based upon the destination information contained in that capsule. But once that connection has been made, then it was fixed for the duration of that communication, as then the capsules would go unseen down that tube to the next circuit you had made. Alternatively, if it's a packet switch network, then again, we have the same setup, but every time a packet arrives, someone's got to look at the label, work out where it goes, and put it down the appropriate tube. And obviously that's a lot more efficient in terms of utilization. But it does come at the cost of a little bit more processing. With circuit switching, you look at it once at the beginning, and then you don't care. With packet switching, you have to make that decision of where this capsule is going every time a new one turns up. So it's a little bit of a trade-off. But in general, packet switching is more efficient, and that's generally speaking the technique we do use. So another quick quiz. So we have one 100 megabits communication channel, and connected to that we have a number of users. So if we're using circuit switching and each user requires a 10 megabits per second data link, how many users could we have if we're using circuit switching? And what would be their maximum and minimum transfer speeds? If on the other hand we're using packet switching, again we have the same 100 megabits per second data link, how many users could we have? And again, what would be their maximum and minimum data speeds? And not to give the game away, you will have to make some assumptions about how these users are using this communication channel. So we use packet switching because most communication is bursty in nature. You transfer something and then your communication network will be idle for a certain amount of time. And obviously if it's idle, we don't want to tie that to one user. We want to release that communication channel to other users so it can be used. So to allow us to send those packets across our network, just like the writing a letter case study, we need to have some sort of address. We need to have some sort of routing information within our packet. And depending if you're transferring the data across a local network or a wide area network, how we represent that information will change. And because of that, we'll use a protocol stack. So rather than having one protocol that does everything, one means of communication that does everything, we break it down into different layers depending where we are within the network. So for this module, we'll be using a 5-layer model. So level 5 is your application interface. So this is how your email client will connect to the network. It will connect through protocols at this level. So for example, SMTP, then we get to our transport layer. So do we need reliable or unreliable connections? I know you say, why do I need an unreliable connection? But we'll look at that one later. But TCP and UDP, Then we have to decide how we route our packets across the network. So we'll be looking at the IP protocol, our network layer. Then on our local network, we'll be using the link protocols. So we'll be looking at how we transfer data across our Ethernet connections and our Ethernet frames. And finally, we'll get down to layer 1, which is the physical layer. So actually, what do the ones and zeros, the actual voltages, look on the wires, and what type of wires do we use? And we'll look at all of those as we go through this module. So as it says at the bottom there, we'll be looking from the application layer, so protocols like HTTP, so the protocols that are used to transfer your web pages, all the way down to your RJ45 physical connectors, the sockets you plug into the back of your computer. So demo time. So in the review session, we'll be going through the actual hardware using. So we'll be using these systems in the labs. So in the labs, we have some hardware which we can build some networks upon. So we need various network devices. So you have a router, there you have a MikroTik router, we have a switch, you have 3 hosts, 3 Raspberry Pis that you can connect to that network. Well, that's not strictly true. Or to expand upon that one, you have 3 Raspberry Pis that can be clients, servers, or routers. So we can configure them in different ways to make more interesting network scenarios. So each Raspberry Pi has 2 network connections. It has its onboard NIC, its onboard network interface controller, and also has a USB to Ethernet adapter. So it has 2 networked interfaces. Because we're running these headless, we're not connecting keyboard and mouses. Connections will be made via a remote desktop via the switch here. So we need a reliable connection that we can always get access to our Raspberry Pis, and we need a connection via the router here, which we can mess around with. And if it breaks, we don't want to be permanently disconnected from our Raspberry Pis. So the remote desktops will be running, and the SSH and the Telnet terminals that will be running will be run across typically this network here. So yeah, we'll look at this in more detail in the review session, and we'll look at some of the software we'll be using. And most of the labs are based around Wireshark. I'm a great believer you really only start to understand how a protocol works when you see it in action. And what Wireshark will allow you to do is capture these packets, or capture the packets being transferred across the network, so you can see actually what happens. Because as always, the subtlety is in the detail. Okay, so in our lab sessions, we'll be building different networks, and you can arrange those different networks in different ways, and there's different topologies, so different ways of connecting machines together. So when I first started, it was mostly buses. So back in the day when you didn't have RJ45 connectors, you had BNC connections and coax cable, you had a bus. So all these machines were connected physically to the same wire. So obviously, if all these machines are connected to the same wire, you can't have multiple transmissions happening at the same time, because you can't obviously drive 2 different voltages onto the same wire at the same time. That'll cause a short circuit. So that was a limitation of that technology. So what we'd say, this type of network topology, it has 1 broadcast domain and 1 collision domain. So collisions occur if 2 things try to transmit at the same time. And to get over those problems, we had different protocols and different techniques to identify when that happened and handle those scenarios in a logical way. An alternative network topology that was around at the same time was a ring. So here, rather than all our machines being connected to the same physical wire, you can see they're connected together in a loop, in a ring. And the way this protocol worked is you had a concept of a token. I always think it's like the early train systems, where a train would pick up a physical token as it entered a section of track. And if that token wasn't available when the next train arrived, then it couldn't progress. So in this scenario here, if a computer had the token, it could transmit. So if machine A wanted to transmit to machine D, it would transmit its packet to B, it would identify that this was for machine D, and it would pass it on, and this would be received. At some point, A would release this token, and then that could be used by a different machine. So this machine here then could start transmitting. So you never got any collisions in this scenario. There was a lot more management of who can transmit and when, organised by that token. As things progressed, different technologies came in. So for our bus system, obviously having 1 physical cable was a little bit unreliable. So if you had a break anywhere in the cable, the whole system would go down. So there was a move to more of a star-based orientation using hubs. So a hub, in some respects, is no different to a bus. It's still 1 collision domain. A hub is a repeater, but it did allow you to connect multiple hosts to a central point using different cables. So if 1 cable broke, the whole network didn't go down. But again, you still had 1 collision domain and 1 broadcast domain. So again, when you're using a hub, only 1 thing can transmit at any one time. But it was more convenient to wire up. Again, things progressed. Silicon got cheaper. So they may look the same, but we moved from hubs to switches. So it's the same wiring. So now this device in the middle here, rather than being a dumb hub, it had some intelligence. It could work out who was communicating to whom. So rather than when a packet was transmitted by machine A, if we were using a hub, it would go to the hub and then be retransmitted to all the machines connected to that network, exactly the same as you would have with a bus. So when one machine transmitted, it would be received by everybody, and you'd work out using the address who was the destination for that data. So with a move to a switch, what happened is the switch can learn who is connected to which port, which physical interface on this switch. So when, again, one machine transmits, so machine A transmits and its destination address is machine D, internally that packet is routed through to the correct port. So it won't be transmitted to machines B and C. So that means machines B and C could communicate at the same time. You've got some intelligence within this switch, and we'll look at this in more detail as we go through the module. Another scenario is if you want to ultimate communication parallelism and reliability, you can go for a mesh. So this is where every machine is connected to every other machine. So you've got multiple communication channels. So if one goes down, there's always an alternative path to a different machine. For the purposes of this module, basically we're looking at stars. So we're looking at machines connected to either switches or routers that connected to other networks or other hosts. But the reason why I'm showing this one here is it does bring into that idea of collision domains and broadcast domains. The easiest way to understand a collision domain is when you had the bus. You had one wire, so you could only have one thing transmitting at any one time. So if you had two machines trying to transmit at the same time, that was a collision. The term broadcast domain is if a machine wants to transmit a packet to everybody and do a broadcast. Again, who can see those packets? Who is on that physical wire? So for a bus, it was one broadcast domain because if somebody transmitted, everybody could receive it. When this is a switch in a star scenario, now each link is a collision domain, but you still have one broadcast domain. So if A wants to broadcast to everybody, the switch knows that it has to repeat the message to each of the machines connected to the switch. But if it's doing a one-to-one communication, as I was saying previously, it will route that directly to the machine that it's going to. So a unicast communication. Again, we'll be looking at collision domains and broadcast domains as we go through this module. So as I was saying at the beginning of this introduction lecture, the exam for the SIS2 networking part of this module is coursework. So at the end of each lab, there will be some assessed questions, and you do those in your own time, write that up in one report, and submit that along with any Python programs that I ask you to write through the VLE as one zip file. The lab sheets are a mix of background material and tasks that you have to do during the lab session, so I'd always recommend that you do read the lab scripts before the lab, and then you maximise your time. You know what you have to do in the lab, you know what tasks you have to perform, so definitely have a look before the lab. The labs are open Monday, Friday, 9 till 5. They're closed in the evening and closed at the weekends. So during the week, work through the assessed questions and the labs at your own pace. But I definitely wouldn't recommend it leaving it all to the end. If you do, it always gets busy at the end of term, people playing catch up. Typically there's only 3 or 4 questions in each lab script, so make sure you do them each week. Don't leave it all to the end of term. But obviously the final write-up you can leave and do that over the holidays, so make sure you've done all the tasks. Don't have to write them up nicely just then. Make sure you've got all your screenshots. Make sure you've tested all your programs work correctly, and then you can write that up at your leisure. So here we have the learning outcomes for this part of the module. As always, they don't really say that much, do they? So they're not that descriptive, really. You could read into any of them, but this module is a hands-on module. We'll be working under Windows and the Raspberry Pi, so that'll be a Linux-flavoured OS. So if you're not familiar with Linux, it might be a good idea to have a little play around with it to get the basics. We'll be using Wireshark extensively and the command line interface to look at the various tools that we have. Ping, traceroute, dig, you name it. And we'll also be writing some programs, some software. And the language we'll be using is Python. I'm afraid no other language is allowed. And for me, the intention of this module is at the end, you will have some basic network engineering skills. You know, you'll be able to use, build, configure and debug some basic networks. Fingers crossed, touch wood. Okay, I think that's where I'll leave it for this week. We'll move on to the next set of lectures where we'll be looking at layer 5, our application layer in our protocol stack.